Hello, this is Britton LaRoche. I'm a staff solutions engineer at Confluent, and today I'd like to talk to you about digital transformation with what I call Kafcongo. That's Kafka, Confluent, and MongoDB. I have a couple of things I'd like to talk to you about. The first is my experience. I started out life as a Java application developer in an Oracle DBA. Did that for about 8 years. I worked for Oracle as an enterprise solutions consultant for about 5 years. I also worked for MongoDB as an advisory solutions architect for about 4 years. I'm MongoDB certified, a developer and a DBA, and I've been with Confluent for about 2 years. And I think this makes me pretty well qualified to talk about all the subject that we're going to cover here. I've actually lived this, I've experienced it, and I have a lot of hands-on application development work directly related to this topic. So the agenda is basically, what's the current state? Why do we need to change? What made me go to MongoDB, and why MongoDB and NoSQL specifically is special? Then what is Kafka? What is Confluent? And then the synergy between Confluent and MongoDB. And this is a very powerful synergy. And I'll talk about where we overlap and where we complement each other very nicely. JB Hunt, I will talk about two specific real-world use cases. JB Hunt was a real-world logistics IoT use case. Toyota Financial Services is a real-world financial services legacy modernization use case. There are a number of companies that I've worked with directly where I've seen this at play, and a handful of names: AT&T, 7-Eleven, Mr. Cooper, JB Hunt, and Toyota Financial Services have successfully transformed their businesses with both MongoDB and Confluent Kafka. I also have a few references here. This is a LinkedIn article I wrote on why I made the move from Oracle to Mongo, and it really talks about the differences between the relational paradigm, and MongoDB and NoSQL. A very good topic. This right here is Rick Houlihan's AWS reInvent presentation, explaining why relational is dead. And I'm 100% in agreement with him, and I will actually cover at a very high level some of the things he covered in his talk, but it's worth watching that video if you get a chance. Real world use cases. I also have a thing where I talk about in detail JB Hunt and Toyota Financial Services. It's a great leave behind with your customers. It's a great thing to talk about. Everything I reference there is publicly referenceable information, so it's great to share. The other thing I have is an article on how to migrate from Oracle to MongoDB Atlas using the Confluent Cloud. And I actually put together an article with a GitHub that actually walks you through step-by-step how to do it with videos and everything. So it's a 90-minute instructional. After a developer completes this, he actually has a working POC in his hands where he can actually go and take this to upper level management. And I wrote this POC and this article based on seeing several customers do the same thing over and over again, where they took open source Apache Kafka and the community edition of MongoDB, and actually tested out a POC where they migrated data in real time from Oracle to MongoDB and kept those instances in sync. Very powerful, something to be aware of. So, current state, let's talk about this. So this is the current state with relational paradigm. You have probably thousands of tables. It's complicated. It's hard to see. It's hard to understand. Developers take time to learn it. It's very hard to find a developer that knows a programming language like Python or Java or Go, and also knows the database and how to write SQL effectively. Typically, there's an object relational mapper and a whole bunch of other things that people use to make sense of this and to actually get their jobs done. That's our current state. The other thing that we've noticed is that we have kind of a bunch of point-to-point integrations. I live this world where I'd be over here, I have an application, help develop a database, and then they want to put that into a data warehouse. Guess what? This other application also wanted to talk back and forth to my database. So a lot of different things. Quickly, my database became a bottleneck, right? The more back office enterprise and lines of businesses that wanted to access my database, the more and more it needed to expand and grow. In addition to that, they would do ETL for the data warehouse. They do ETL to other databases. And the thing about this is that it becomes kind of a nightmare to make a change. If you make a change in one system, that has to be propagated to all the other systems. And a real world example, Toyota Motors North America could not sell a car that cost more than $100,000 for 6 months because of all the changes they had to make to go from $99,999 to $100,000 plus. And all these systems had to be updated. So it kind of shows you the pain once it's up and running. Not only is it difficult to maintain all these point-to-point integrations, just connecting it over the network, but my gosh, all of the complexity involved. I've had customers tell me that they're afraid to make a change because it will break something and they know it's somewhere and they just don't know how or where it's going to break. So that's a very brittle architecture with a lot of tech debt, with a lot of pain involved. And we see this everywhere. This is the current state for everyone that has not fully digitally transformed and gotten rid of some of their legacy code. Also, getting rid of the legacy code isn't necessarily the only way to do it. You can actually work where you have some legacy applications and modernize at the same time, and I'll show you how that's done. So this is kind of interesting. This is from a Gartner article, and it was basically the DBMS market share over a 5-year period from 2017 to 2021. And this is really what we take a look at. If you look at the far right, in 2021, the blue is cloud revenue, cloud database revenue, and it is on par with the actual on-prem revenue. So in that 5-year period, we had basically every line is about $5 billion. We had about 5 or 6 billion in 2017 and about 40 billion in 2021. It actually caught up, and now we believe, I'm waiting for the numbers. There's a couple of reports that are out there that I can't wait to get my hands on that actually say what happened in 2022. I would believe that the cloud exceeds on-prem at this point. But the interesting thing was that it literally doubled the size of the database market in 5 years. So cloud databases is a big thing for a lot of companies. And it's a good thing for everyone. Doubling the size of a market shows that there's an increased demand for data. So in that same time period, I want to call out a few things. The orange line is basically AWS, and they actually were able to grow from 10% to just under 30% in that same time period, about 2017 to 2022. Oracle database declined from about 36%, and as far as the article was concerned, it was 20.6%. Some of the other articles that I've seen show around 16% of the market share, total database market share. So they went from king to third place at best. It's kind of interesting to see, as we look at here, we also see that Microsoft Azure was kind of flat through this, or at least the Microsoft databases. So Microsoft kind of stayed at around 20%. If you look through the chart and everything. Again, Gartner article on the total is called DBMS Market Transformation 2021, the big picture. Highly recommend it. The interesting thing is, why did we see this trend? What's happening? And I think that you'll see that this is marking the doubling in size. One of the things contributed to that of the database market, mainly because AWS offered some really good cloud databases, and Oracle pretty much stayed on-prem or had its own cloud that very few people adopted. So let's take a look at Oracle. Oracle was released in 1979. In 1979, this is a 250 megabyte hard drive. And you can see it's about 4 feet tall and about 2.5, 3 feet wide. This hard drive from 1979 contained 250 megabytes worth of data. In 1979, disk space was expensive. It was complex. And a fellow by the name of Edgar F. Codd wrote a white paper on relational design. And what you could do is you could break down repeating values and have a primary key joined to a foreign key in another quote unquote table that allowed you just to repeat only the primary key as a foreign key in the table. So things like customer name and address and things of that nature that would be repeated is not just the key value of that customer. So the customer's first and last name isn't repeated. That was done to save on disk space. And that was when Oracle was born. It was the first relational database, the actual implementation. Oracle and Larry Ellison got a contract from the government to develop it, and the rest is history. It has been wildly successful over the past 40 years. So it's kind of interesting to see what it looked like in 1979. That disk drive The modern phones now, you can get 512 gigabytes on your phone, which you carry around in your pocket. That would have been 2,048 of these large disk drives. No way you could carry that around in your pocket in 1979, but it shows you the transition from disk space being incredibly expensive and high tech to something that's really a commodity. Disk space is not anything to worry about these days. So we're going to talk about Moore's law and nanometers, and it's really kind of interesting. As of May 2021, IBM and some of the silicon manufacturers in Taiwan came up with the first 2 nanometer chip, and you can actually see what that looks like. These little gaps in here, these little where we actually see the 3 lines going down, that is about 2 nanometers wide, which is a total of like 10 silicon atoms. You can basically almost see the little silicon atoms there. The interesting thing is you cannot really go beyond that length. You can't get smaller. And the interesting thing about that is why? Well, quantum physics comes into play. And so you have a deformation on the crystal or something that happens, and the overflow of current that you don't have the ability to really have reliable processing. What does this mean? That means in 2021, we have literally reached the limits of silicon. It means that you cannot do computational processing any faster, anymore on silicon. And what's that mean? Well, Moore's law, up until recently, pretty much kept in track with what they call sysmore. And they were pretty much the same. Every 18 to 24 months, the processor size shrank to about half and the power doubled. Well, when you reach the limits of silicon, Moore's law is not going to play that way. There really isn't much you can do other than create new cores and try to run parallel processes on cores. And that's where you have the sysmore coming into play to try to keep up to that. There may be other technologies other than silicon that allows us to get smaller and faster, but we've kind of hit the limits of silicon. So there is a problem here. Why is this important? Why is CPU processing important? Well, we're going to talk about the CPU processing becoming the bottleneck and disk space not becoming the bottleneck when it comes to computation and processing. So let's talk about a zettabyte. What is a zettabyte? Well, that's basically 1 with 21 zeros behind it. It's a large number of bytes. So a kilobyte is 1,000 bytes. A megabyte is 1,000 kilobytes. So you have megabyte, gigabyte, terabyte. And then after that, we have petabytes. After petabytes, we have exabytes, and then we have zettabytes. So a zettabyte is 1 billion terabytes. That's a lot of data. And if we take a look at the IDC size of the global data sphere, we can see that in 2010, we had about 1.5, 2 terabytes, 2 zettabytes. In the year 2025, we expect 175 zettabytes. So what we see is this incredible growth of data. So we have not just a few rows of data or a few documents to look at, but millions, billions of documents. And all of this is being generated by handheld devices like the mobile devices that we have. We have IoT information that's coming in. We have user data, clicks over the web. Everything that can be tracked is being tracked, and it has value. Data has value. And so we're storing this data. We're analyzing it. We're processing it. We're doing machine learning against it. And we're not slowing down. We're getting more and more of this data. And why? Well, disk space is cheap. We can store that data. Accessing the data is now the problem because we have reached the limits of silicon. So this is a great talk track that was done by Rick Houlihan. He worked at AWS, and he was in charge of Project Rolling Stone, which removed all Oracle database management systems from Amazon internal systems. And he explains that the problem with relational databases are that they use complex joins where they compare that primary key to a foreign key. That is a CPU intensive operation to be able to scan that and find out where there's a match. That has to be done computationally, which means they hit right on the bottleneck of silicon processing. And so the end has come to Moore's law. However, storage is incredibly cheap. So we've kind of seen a total shift in the paradigm since 1979.
Hello, everybody.
And so this
welcome.
is a link to the actual video. You can feel free to watch that on your own terms. So relational is pretty much dead, and everyone understands this, including Oracle. So one of the things that they've been asked for over and over again by their customers is, please allow our developers not to have to write SQL queries. Allow them to retrieve the data as a JSON document. And they have done this. In Oracle 23c, data can be accessed as a JSON document to deliver the application simplicity of documents. Everyone wants this. That's great. What's the problem? The problem is that even in Oracle 23c, data is still stored as rows and tables. And they say to provide the benefits of a relational model. The problem with that is that's expensive for computational purposes. When we've reached the end of silicon, the last thing we want to do is actually do a join across multiple tables with billions of rows of data. Relational doesn't do this, and they haven't really adopted a full-on document database to make sure that things are as the developer wants and efficiently queried against the database and stored in the database. So they're taking a step toward it, but they are decades behind MongoDB and other document databases. MongoDB came out in 2008, so they have a whole bunch of development that has gone on since their first iteration. So I always think about Dr. Evil when we talk about 100 billion or a million or whatever. And he says, so you got relational data, huh? How about 100 billion rows? Well, I tell you what, with 100 billion rows of data, I guarantee you that a 5-table join will never return. That you cannot join 5 tables together. I know from experience, you got to do something different. What do you have to do? You have to basically take that data from the operational database, create an ETL process, and load it into a data warehouse. What's special about a data warehouse is typically you have what's known as a star schema, which means that you have dimension tables, and then you have a fact table, a denormalized fact table that gobbles up disk space, but it only has 1 or 2 joins. So I can join from a dimension of time, or maybe a dimension of region, and I can get my sales by region by quarter by querying this data warehouse. Interesting enough that that's still not fast enough. You usually put that into an OLAP server that builds a cube, and then you could do your data analysis on it. So it's like a 3-step process to be able to make sense of data from a relational paradigm. And then they actually do some more ETL from the data warehouse to different data marts in a meta repository. Why? Relational is not computationally effective. It never has been. This has been discovered in the 1990s. Instead of rewriting the database, they just rewrote their applications to denormalize data and to take advantage of things that would make performance faster. And this is a painful process. Not only is it expensive and time consuming to write all the ETL, but it's brittle and it has to be updated and maintained, and it's slow. It takes hours. Typically, you don't want to run this in production because the relational database is struggling to keep up with production loads. You run it at night in a batch process. So you usually get your information a day or 2 later. That's a problem. So let's talk about MongoDB. You go from this object relational mapping layer, where you go from a customer to multiple tables and an opportunity, for example, and things of that nature, broken down into many tables, into where we have the actual joins from customer ID, primary key, to customer ID for the address, for the phone. You have to join these tables together. And as I said, does not work well when you have a 5-table join. Typically, you want to go to demographics, maybe interests, maybe some of his customer orders, and suddenly your relational database doesn't work anymore. So that's the problem. So you go from that to this, where you have a customer object mapping to a customer object. It's basically a JSON document that the developer works with, and that's what's stored in the database. No join. I look for customer ID. I find that it's indexed. I pull back the document that has his address and phone number. What do you know? It's all in one place. Great, super fast. So this is what it looks like. I have multiple billing addresses. I have, multiple address types. I've got a billing address and a shipping address. I have multiple phone numbers, but it's all in one document. Everything that I need, no joins. Super fast, very efficient. So let's talk about event-driven architectures. Again, we talked about the slow batch processing and the fact that this is not real-time data. And you get some analysis and things of that nature, and you find out days later that you made some horrible mistakes and lost millions of dollars. That's really not acceptable in today's economy. And if your competitors can respond immediately to this and it takes you several days, they're going to make money while you lose money. And that's what happens over time. Very few of the Fortune 500 have stayed in business over the past decade. A lot of them are getting squeezed out. They're no longer in the Fortune 500. I forget the exact number, but it's something like 80 or 90%. It's crazy, crazy high. So take a look at this. This is the maximum value paradigm that we're talking about. And why is this? Near real time, I can do preventative or predictive things. I can make time critical decisions. I can take action within a few seconds. But after a few minutes, I'm reactive. And obviously, after hours or days, this is where the traditional business intelligence from the batch processing occurs. It's days, it's historical data. This is the past. There's nothing you can do to it. You can't react. You can't take action. You can't do any predictions, nothing. So imagine someone checking out AT&T, for example. They saved over $1.2 billion in 2019 with MongoDB and Confluent or Kafka, if you will, basically with a fraud detection system. So and this is in retail, it was in stores, it was, home, business, everything. And they could detect in real time if someone who was buying an iPhone at an AT&T store was really not the Bob Jones he said he was. And they could do this by looking at things in real time, looking at Bob Jones' purchase history, looking at his last purchase, where he was. And he's basically going from Brazil to Chicago. It sounds very bizarre that he's traveled that quickly. Is that something that we should flag as a fraud? You can do that in real time. You can check to see if that's actionable and stop. Right? I can actually stop that transaction and say, I'm sorry, sir, but you'll need a second form of identification, blah, blah, blah. And you don't find out minutes or hours later or a day later that you were robbed, right? You just lost money. And that's just one simple example of fraud detection and things that need to be corrected as they occur. So this value of data is far greater than this value of data. But this historical data does have value. It allows you to do trends and predictions. You might find by looking at the historical data that, in fact, Bob Jones does travel to Brazil twice a year. And this is typically the time he does. Maybe this is the real Bob Jones. So it allows you to actually go and take a look and make an intelligent decision in real time. But you need both. You need the real-time data and a comparison to the historical data to build a really actionable and correct machine learning model, for example. So would you cross the street with traffic data that was 5 minutes old? No, definitely not. You want to know where the car is immediately. And so things like Uber and Lyft, they actually use Kafka under the covers. You can actually see in real time where your driver is and make decisions. You're not like in the old days of calling up for a taxi and waiting on the curb, just hoping that someone will show up. You see in real time what everything is, where they are, and how close they are to you. It allows you to make decisions and decide both on pricing or multiple apps. You can use a curb app now for the taxis these days. You can switch between Lyft and Uber if you're not satisfied. It allows you to get your job done efficiently. But more importantly, that same technology can allow you to make a decision, a mission critical decision with relevant data in real time. So what is an event? Well, an event is everything. A sensor in Carol's car detected low tire pressure. That's an event. We put that into Kafka. And basically, Kafka is a log of events. And events are things that you want to know what happened in the world. A transaction, Alice sent $250 to Bob, right? We want to know about that. Fujifilm camera was shipped. Hey, let's notify Sabine that her order's on the way. These type of things are events. It's how you define something of interest data-wise that you want to keep track of. And this is in an order sequence, and it's put into Kafka. Kafka persists that log and can be consumed by multiple applications. One log, one place to go to see everything in real time. So remember when we talked about the line of businesses and the fact it took 7 months to make a change to all the data because of all the different places and things, how things are connected, and the fear of making a change that would break downstream systems and all the interconnectedness and the fact that these things become bottlenecks. You go from that to this, where you have basically a central nervous system where everything, instead of the application communicating with the database, it communicates with Kafka, and Kafka updates the database in real time. If we have data from this database, as changes occur here in real time, it's captured through what we call connector, the connector architecture. We capture the CDC information, put it into a log, and we can update not one, but multiple data warehouses, not overnight, not days later, but in real time. So your dashboards, your reports, and everything are up to date. Imagine being able to see things in real time and be able to respond to changes in maybe a marketing campaign or things of that nature. You can enhance and correct as you see the data flowing. This is a beautiful architecture. I've had lots of people ask, well, isn't this a bottleneck? It would be if it wasn't horizontally scalable. We actually have the ability to process, and we do, over 11 billion events at Walmart. And that data is actually, if you go to the Walmart app and you look for the Dave's Killer Bread on aisle A6 or whatever, it's there. It shows you how much is there and it's updated in real time. As the trucks are scanned and the inventory is there, we know where that the deliveries have been made, and we know the inventory in that store in real time. That's how Walmart runs its business, and it's using the Confluent technology behind the scenes to do that. And it is horizontally scalable. I seriously doubt, unless you're Walmart, that you're going to have 11 billion events a day. You could, and we will match that. And you can go higher than that. We have a number of customers that are running their entire business on Confluent. So not a bottleneck, definitely scalable. So let's talk about Kafcongo. This is the synergy between MongoDB and Confluent. And we talked about modern architectures, data flowing in real time. We talked about the limits of silicon being reached and the need to store immense amounts of data and query it effectively and efficiently. So everywhere that you have MongoDB, you have Confluent, which is really nice because you have open source offerings on both sides. You have a community edition of MongoDB. You have open source Apache Kafka on the Confluent side. If you want to run on premises, you have the enterprise edition as well as community, and the same for Confluent. We have Confluent platform that runs on premises. If you have a hybrid implementation, that works well too. You can have MongoDB speaking to MongoDB Atlas and have on-prem and cloud-based solutions working very well. Same with Confluent. You can have a Confluent platform on-prem and a hybrid solution where it's talking to, through cluster linking, to the Confluent cloud. And so if you want to run the cloud, yes, we have MongoDB Atlas in the cloud. We have Confluent in the cloud. And we have AWS, GCP, and Azure. Yes, Confluent's in the same regions in AWS, GCP, and Azure, all the three major cloud providers. And we have the ability to, in MongoDB, replicate data from AWS to GCP, for example, and the same thing with Confluent. So we can actually run in AWS and GCP simultaneously and be right there together. So MongoDB and Confluent run everywhere together, and they communicate with each other in real time. Why? MongoDB has a source connector, and there's some other exciting things I can't say in this presentation that I will talk about later, but the relationship between Confluent and MongoDB is strengthening, both from the sales teams and by the technology, so that sourcing and syncing data from Confluent will be faster and more efficient. Today, we have the ability to source and sync with the connector architecture. Within a few minutes, you can spin up a connector and source data from MongoDB. As things occur in Mongo, you're notified in Confluent, and we can update other systems. A lot of our customers are doing data from Confluent, from MongoDB into Confluent, and then using a Snowflake connector or a BigQuery connector for the data warehouse application. MongoDB is an awesome transactional database, and I can't recommend it enough for something to be in front of a large data warehouse. MongoDB even has the capabilities, many capabilities that exist in a data warehouse. But for the columnar reporting and things of that nature, Snowflake, and Google BigQuery are great, and that's really popular with our customers. Important thing, data that comes from Confluent can be synced into MongoDB. So a change in Oracle or a change in SQL Server can pump that data straight into Mongo, make it easy for your developers to get information and to build like a customer 360 across multiple systems. You might have your order and shipping information in SQL Server. You might have your returns and order items in Oracle, and you might have your demographic information somewhere else. And we can join that data in Confluent and then create a document that updates MongoDB. Then you go to Mongo to see everything about that customer, how many returns they've had, what's their customer satisfaction, how much they buy over a period of time, all your reporting, dashboards, and analytics running off Mongo. Beautiful, beautiful architecture. And I've seen that in many companies. So how does this work? Well, MongoDB has this concept of change streams. So as data from different things flow into Mongo, and we update a collection, there's a change stream API that allows you to do real-time notifications. And you can do things like MongoDB triggers. You can do things like notify other applications, or you can actually use the connector, and you don't have to custom write a listener for the change stream API, because that's what the connector does. It puts it straight into Confluent Cloud, into Kafka. So you're able to build reactive real-time services super fast. And this is not a small lift. This is a heavy lift, but it's very easy to do. When I first started playing with this, I was able to set up my first connector and actually put data into Confluent within 5 minutes. And it made a great demo on the sales side to be able to show how this works. So not only do you have the ability to source the data through change streams into the Confluent cluster, but we can have the ability to sync the data from Confluent. So topics A, B, and C, this may be customer demographics, this may be customer orders, this could be returns. And I can see all of this together, create a document, put that into the MongoDB connector, and then update a MongoDB collection all in real time. So again, data transfer between the two, super powerful. This is kind of an amalgamation of a number of banks, financial services, and other places that have done legacy modernization. I'll talk about Toyota Financial Services and what they did, and it's very, very similar. For example, account validation, payment processing, and check clearing may be done in a banking system that updates an IBM mainframe when a customer makes a payment. This could then go to a nightly batch process with Oracle, and we can update the Confluent Cloud as that batch process is run. But that's not the best way to do it. Wouldn't it be great to use something like NiFi or Click, or the DB2I CDC Infosphere from IBM, and the IBM CDC Kafka agent? So as data changed on that IBM Z series mainframe, it was in real time updated into the Confluent Cloud. What's that do? That allows us to do things like update the Salesforce information, where they send out dunning notices to customers and things of that nature, to apply that payment and let that payment be applied in real time, to notify MongoDB Atlas for customer systems to come in and verify their payments was done, or that their things that were happening. They could write their own reports against MongoDB Atlas, and they get the whole slew of architecture behind the scenes. You can have custom microservices running in the cloud that is able to do this. Now, notice what we did. We offloaded the reads only. But look at all the beauty that comes out of that. We have third-party systems come in and check the credit score and the payments of your customers in real time. It's a new service that you can offer. And all of this is cloud-based. So we did legacy modernization. You notice that 60 to 70%, and this is across the board, my experience with the customers, 60 to 70% of the mainframe MIPS are not writes. They're reads. The vast majority of what's going on is reads. So we write the payment once, and then everyone reads it to see, was that payment applied? When did it come in? All that kind of stuff, all these different applications. So by moving it to the cloud and offloading the reads to MongoDB Atlas and to Confluent for the real-time stuff, we offloaded 60 to 70% of the mainframe MIPS. Typically, this pays for the modernization effort right off the bat. It pays for the Confluent Cloud and MongoDB Atlas handsomely with cost savings. So this is something that you can approach your customers that are running on mainframes or AS400s or things of that nature, and give them an easy path for legacy modernization within a few weeks, maybe a few months at most. This is a very easy thing to do. And I've seen this replicated across many customers. And we'll talk about a couple in a second. So Confluent Kafka puts data in motion across the enterprise and allows you to make decisions on those events as they occur in real time. That's super powerful. And it updates other systems. So if something happens, we get that information. And you have the ability to process this as it occurs, make a decision with stream processing and things of that nature. Super powerful. MongoDB allows you to look at everything from what's happening right now to what the history of that event is. You get the ability to see the full picture in Mongo, and you get to query it efficiently in a way that doesn't break the CPU, right? That's very effective on the CPU. Oracle, for example, is licensed by core. They know where they're hitting and where customers need that information. They know that the cores are going to be processing the joins. It's going to be expensive. They license by core for that reason. MongoDB, it has very little CPU impact. It is ability to pull the data back based on indexing alone, and you go to one document that contains all your information. Beautiful, beautiful. The two together captures the entire data life cycle of an event, right? I can see what happens in real time, and I know that Bob Jones travels to Brazil. It's probably Bob, right? This is his pattern. How do I know it's his pattern? Because I have the history. I can make a real-time decision because I see the event coming in, trying to buy an iPhone, and I know Bob. I know his entire history. I can make a really super intelligent decision and be very accurate and know that this is fraud or not. Why? Because I have the complete picture. I have the full data life cycle. This is incredibly important. MongoDB is not a stream processing engine. They use us for technology. With KSQL or Flink SQL or all that other stuff, we're not going to contain the entire history and allow you to do reporting and dashboards and things of that nature. MongoDB does not compete at all with the Confluent Cloud. We are 100% complementary products. We have the ability to make real-time decisions, things of that nature. Use Flink SQL, for example, to look at things over a period of time, but typically we have a retention period of 7 days. If you want Bob's entire history over 2 years, this is where to get it. And fast and effective in MongoDB. This is beauty. This is super powerful. What's that do? It allows you to basically, the connector architecture allows you to get that data in and out super fast between the two and make decisions and analytics and visualizations across multiple lines of business and see the entire history. But more importantly, the developer now has full access to real-time events and the ability to query all relevant data to solve business problems. Everything the developer needs is at his fingertips with these two technologies. And that enables your developer to rapidly prototype and create applications like never before. It rids him of all the tech debt that he's had to suffer through in the past. So let's talk about J.B. Hunt. J.B. Hunt is a transport services company. It was created in 1961 in Lowell, Arkansas. It's still there. Today, it's over $3.7 billion. And it's basically transportation delivery services to a great number of customers in the United States, Canada, and Mexico. Great stuff. Good company. And they had an interesting challenge. They wanted to get real-time IoT information from the driver, from the truck itself, and from the container. This is the container on the back. And they wanted to do a joint business venture with BNSF Railway, where they could actually have a driver deliver it to a train, this container get loaded on the train, have it transported across the country, and then offloaded, and yet another driver would come to pick that up. So this is the BNSF intermodal, what they call it, with J.B. Hunt. Pulling these little trailers across, or containers across the country. And the tech stack is really cool because along this way, imagine that Ben & Jerry's in Atlanta, Georgia is shipping some ice cream to Walmart stores in California. It's going across the entire country. And they want to have that temperature of the ice cream below 40 degrees at all time. So being able to see that information in real time is important. If, for example, this was still on a truck and the refrigeration unit on this container, the fuse blew, you could notify the driver to go up there and check that fuse and fix it. Or maybe you left the door open, but the temperature went above a certain threshold. Or if the driver's on the wrong path, you can alert the driver that he's going to the wrong Walmart store. Or if he's delayed in traffic, the train knows that he's not going to make that train. They can reschedule and put him on another train. The driver that's picking it up knows where they are. So GPS information, those type of things, super powerful. It enables a whole new business, enabled Shipper 360 at J.B. Hunt. And this is pretty much how they do this. The telemetry data is shipped to on-prem, where they have telemetry enrichment to make sense out of that. They push it into Confluent Kafka. They use the MongoDB connector. And so we get customer reports and analytics for the customers that want to log in and see, the ice cream was reported melted at a particular Walmart in California. We don't know if that happened on the truck or if it happened in the store. And so they can query this. And because MongoDB Atlas, all the real-time event notification is here. If the truck's going to the wrong place or there's a temperature variation, the driver's aware of it in real time. But for that whole trip, what happened? Where did it melt? So the customer can log in with the secondary indexes and time series database. The whole history of that trip is recorded, and they could see if something went wrong, and they know where it went wrong. Not because they know the driver ID or they know the device ID or they know any of this information, but because they know their shipping ID, and MongoDB has secondary indexes with a time series database. They can see the entire shipment across the country and every time and all the temperatures. So they can either A, verify that no, the ice cream melted when it got to Walmart, or B, yes, there was a problem and it was while it was being shipped on the train, for example, the temperature went to 80 degrees. So you've got your answer. The customer's happy, maybe not with the ice cream melted, but at least the answer is provided. And MongoDB gave the history. Confluent Cloud gave the real-time information, enabling a whole new business strategy for JB Hunt. So again, between the two technologies, you get the entire thing set up. This is a great video with Donovan talking about this exact thing. It's publicly referenceable, and you can see the entire presentation if you want on this particular slide. I'm going to actually go to the next slide. Toyota Financial Services. This is an actual real use case, and I'm going to fly through this pretty quickly just so you guys get a picture of it. But you basically sell like high-end Lexuses and Toyotas and things of that nature to people that, especially with the high-end Lexus, that may be a vice president of a company. They may be, in other words, their credit score is very important to them. So Mr. Lasso writes a check for his for his car payment. It goes to the bank, it's processed, and say his payment's due on the 1st, so he pays on the 27th. It goes to a mainframe to be processed, and then it goes to an Oracle batch process that then updates Salesforce. Now, actually, before, I think it was 2018, 2017, 2016, around that time frame, the Oracle batch process was taking longer than 24 hours, and it would get behind, and then it couldn't catch up. And so it could be days before that payment was posted to Salesforce. So they would get a past due notice, and that would be sent to the customer, who was furious. And they had lots of phone calls. This was a problem. Toyota Financial Services is an interesting company. They typically have managers that work for Toyota, and then they have systems integrators that actually do all the implementation for them and things of that nature. So they said they got a problem. They went to one of their SIs, and the SI said, look, man, you got a legacy system. There's technical limitations. It's a higher cost of maintenance. You have some data loss. You got lower performance. This is what's causing your problem. What you want to do is modernize your system to a scalable application. It'll have lower maintenance costs. It's more efficient, better performance. You want to do this. You want to do legacy modernization. Probably want to go to the cloud. And so they said, okay, well, what's that going to be? And so again, Dr. Evil, how about $100 million? It was more than 100 million. It was really around 250 million. And so Toyota Financial Services said, here you go, take my money. Here's 250 million. Knock it out. Let's get better. And so about 18 months passed, and they literally had nothing. And why did they have nothing? Pretty much they tried legacy tools and technologies, things like Informatica, TIBCO, whatever, you name it, right? Those things did not solve the problem. And so the question is, after this monumental failure, $250 million, did anyone notice? The answer is yes. Akio Toyoda, his Toyota is pronounced with a D, Toyota, basically is the grandson of the man who started the entire organization, Kiichiro Toyota, and inherited it from his father, Soichiro Toyota. This guy noticed, head of Toyota. He really noticed the $250 million burn. And so he went and tackled his technical ninja and said, hey, man, I need to go fix this problem. I need to go to the United States, to Plano, Texas, to the headquarters, find out what's going on and fix it. And so Izumi-san basically took the information, decided that he would talk to his SIs, say that he's coming to figure out what's going on. And he wanted no one to know. He was going to basically blend into the shadows and just be an observer until he could figure out what was going on. So he hopped on a plane, went over here to Toyota Motors North America. And the best way to let everyone know that something is happening is to tell them it's a secret, because everyone knew about it, including at the time I was working for MongoDB, the sales rep's wife knew who Izumi-san was. So he landed in Toyota Motors North America, As he walked through the lobby, we said, "Hey, Izumi-san." He looked around, kind of startled. Didn't know who we were. The rep actually sent him firstname.lastname@toyota.com an email, and he took a meeting with us, not so much because he was interested in our technology, but because he wanted to know who gave him who gave us his email. And the rep said, "Well, everyone knows that you're here and why you're here. I just guessed," and he was telling the truth. It was firstname.lastname@toyota.com. And he was right. So what Izumi-san was thinking was he needed something different, but he didn't know what it was. He just needed something new because the legacy modernization doesn't work with legacy tools. Infosys had put together a design that used MongoDB and Confluent talking to the mainframe in real time with a series of microservices that would talk to multiple systems, create a customer 360, and provide real-time payment information. It was different. Ken Schulke saw this diagram. He liked it. He presented it to Izumi-san, and Izumi-san said, "Yeah, this is the way to go." So this is from a presentation. I did not put this together. This is directly from IBM. Toyota took the information from Infosys, gave it to IBM. IBM was going to implement it and get data off the mainframe. They used NiFi to actually get this, what they call the Edge Gateway Ambassador, is basically talking. NiFi was talking to the mainframe. They used ISDIO and microservices to route the traffic and all that good stuff, and talk to Kafka, which is Confluent in the cloud. They went to AWS, now on MongoDB Atlas. And basically, with all this information, they were able to get the product information from different systems, the contract, the account, the vehicle information, the dealer information, the customer, the insurance information, the GL, and other information, all in one place in MongoDB. And so the payment would come in, flow in real time, and update Salesforce. It was beautiful architecture. It really worked well. It worked so well, and they were so happy with it that they actually went, and this is Ken Schulke was the manager. Slobodan was the guy who actually implemented it. Izumi-san was on stage with these guys. It was so successful that they were able to actually brand this Toyota Financial Services application and sell it to Mazda. So if you go to Mazda and buy a car and use their financing behind the scenes, it's been rebranded. You're using Toyota Financial Services and this very system that was developed. Beautiful system, beautiful architecture, allowed them to actually offload all the reads to the cloud, and it allowed them to modernize their applications, still having the mainframe, but getting rid of the Oracle batch process, getting rid of Oracle. It was gone. So everything is now real-time, hyper-scalable, very fast, very efficient. MongoDB, real-time information flowing through Confluent, literally transformed the business. And so again, this is how it was done. We have other customers that use, they use NiFi. We have other customers that use the IBM Kafka agent and the DB2I CDC, which reads the DB2 logs. We have other customers that use Click, getting this data in. But what went away? Oh, Mr. Slow bottom Oracle that has reached its limitations. And I'm not talking just Oracle, but Postgres, SQL Server, MySQL. All relational data is dead. It is a bottleneck, and it will go away quickly. The mainframes keep up because they're, even though they're a monolithic architecture, they get upgraded. I don't know if they're going to reach problems with the limits of silicon, maybe not, who knows. But Oracle in relational data definitely has. They're gone. So this is a beautiful architecture. This works at a number of customers, and I see more and more customers embracing this technology. This is Toyota. This is a great thing. Ken Schulke actually goes through, talks about Toyota Financial Services.
To transform ourselves from a company that buys software to a company that develops software. What we're heading for.
And so he talks about Agile Scrum development, everything that rebranding the thing. It's just a great interview. It's on the MongoDB website. I have a link here for the video. Highly recommend watching it. It's just great stuff. It's exactly what we talked about, and it really did transform their business. So the other thing I want to talk about, this is the last piece of it. This POC was done at 5 different customers that I'm working with, where they basically took all the joins, put it into a materialized view or a view, and then had the JDBC source connector. We also have an Oracle CDC source connector that actually looks at the logs, things of that nature. JDBC connector is very relatively cheap, works very well. It does some polling, so it polls like by default every 5 seconds. The CDC stuff gives you stuff in real time, depending on what you want to do and how you want to go. You can use a blend of both. You don't have to use one or the other. Create multiple views against the data. Once it comes in, that customer order information is all put into a JSON document, multiple tables, nice JSON document, MongoDB sync connector, and boom, you got your customer orders or customer payments, customer 360, all that good stuff. This POC can be done in 90 minutes, and I have a GitHub link to it. And it is the beginning of that 5 phases of application modernization, where we offload the reads to start. And this is where we begin. And then we begin offloading writes. I haven't covered that in this topic, but you can. So anything that loads data into the mainframe also loads data into Confluent. We put it in MongoDB. And then the system of transaction is really Mongo. And the system of record is finally Mongo. And so then you can unplug, in some cases, like the Oracle databases. In other cases, you can unplug the mainframe and actually have a fully modernized solution. This is the beautiful thing about MongoDB and Confluent working together. We can talk to all the different systems of record, all the different sources of truth, and legacy systems, put that into highly available, persistent, scalable topics, have a bridge to cloud with Confluent platform, and basically the ability to do cluster linking, so hybrid, all that good stuff if you want to do that, bidirectional sync back and forth through these systems, stream processing, being able to make intelligent decisions. We have a schema registry. I didn't even talk about that. I can't believe I didn't talk about that, but we have a schema across all the systems that are shared, and that's shared in Mongo as well as other systems. That is one place to go. So that $100,000 change, 99,000 to 100, updated in one place. Everyone's now aware of it. You're done, right? Everything is a new version of that schema, and you control the consumers that consume that data and what schema they're using, what version. It's a very easy way to go and make your changes moving forward. And then you get into MongoDB with the primary and secondaries, where they have replicated, highly available, highly scalable architectures. Anything you want to do with analytics, anything you want to do with, they have basically tiering and data warehouse archiving and things of that nature. And they have the full text search capabilities, a mobile sync, team collaboration, the BI connector, and all sorts of charts and graphs that you can do that, personalized marketing, everything. So you get this beautiful real-time scalable architecture that's cloud native, that runs across all the cloud providers in multiple availability zones, which is something that relational databases have trouble with. You usually have an active passive, or maybe you have an active with one online for read only, that type of thing. It's not fully enabled, and it's expensive, and you lose AZs all the time. They don't even have a concept across region. Those type of things, all handled by Confluent and MongoDB. It's cloud native. It's how it was built. It was born. It's really, really, really good. So the POC that I have, that was in that link that I had given earlier. This is what happens. The pieces in the POC is really just the black lines. We have a point of sale system. We create an Oracle a thing that's actually getting data into an Oracle database, set up the JDBC connector, set up the MongoDB connector, and then you can do the customer reports and things of that nature. This takes like 90 minutes to actually show how you can get data from Oracle into MongoDB Atlas. Strongly recommend it. I have some other components that I've added in that actually updates the Confluent Cloud, puts that into MongoDB, to the point of sale system, and then pipes it into Oracle, which then updates MongoDB Atlas. I have another version that's coming out that's going to be GraphQL based, that actually is the next generation point of sale system that updates MongoDB Atlas, puts that in Confluent, and then actually goes and updates old Oracle just to keep it in line, because we find that a lot of customers, it takes time to replace, maybe a few months, and they want to be able to reconcile across the systems and keep everything in sync. So the red lines are coming. The black lines exist as part of that POC that I put together. I hope this is helpful to you guys. And that pretty much is the whole Kafcongo speech. I'm more than happy to run this by or create a custom one for your customers. More than happy to talk to you about anything else that you may have questions on. Feel free to contact me. Again, Britton LaRoche at Confluent, or B LaRoche at confluent.io. Wish you well. Thanks. Bye.